have Team Band, and their idea is a motion-activated wearable that helps simplify communication for non-verbal children. So could we please have Team Band?
I believe the slides are our slides are the ones before this.
Okay, sorry, give us a second. Maybe Team Ben, you guys could introduce yourselves first, like your team members, and maybe just briefly run us through what your project is about. I mean, your product's about.
Sure. So good afternoon, everyone. We are Team Ben. We are Grove NUS students, made out of myself, Agnes, Hong, and Emily is not with us because she's busy with a test. So we'll be presenting on our solution of a motion-activated wearable for simple communication.
Okay, your slides are up.
Okay, thank you. So I'll first be presenting the problem statement and how we went about breaking it down. Agnes will be presenting on our ideation process, and lastly, Johong will be presenting on our prototype and potential improvements that can be made. Our problem statement is to come up with a wearable communication device for non-verbal students with extreme gross motor problems. Some students from our community partner, the Melbourne Specialist International School, cannot speak and cannot move their arms or legs. This makes it difficult for them to articulate and communicate yes or no answers. Other solutions of using simple buttons of different colors mounted on tables have been attempted, but have often come into difficulties mounting them where the students can easily push them, since different students have different limitations. We are looking for a flexible and wearable solution so that even students with extremely limited physical mobility can use it to communicate yes or no. Considering the problem, the expected outcome will be to create a wearable device to communicate simple yes or no answers, which is accessible to someone who can't control their upper or lower limbs. To gather more information about beneficiaries, a site visit to the Melbourne Specialist International School was conducted. It was found that for these students with limited mobility, the interaction with teachers was often one-to-one. They were also able to move their arms quite freely, but this was often with little control. Other than their arms, they found it difficult to move the rest of their limbs. Considering these factors, we came up with a proposed solution, which Agnes will now go through.
Thank you, Jeff. After analyzing the situation, our proposed solution is to use microbit and create a wearable band. This wearable band senses different types of motions and produces a line sound according to each style of motion. The band can be worn on the wrist or where it's suitable for the user, and there are 5 different motion inputs. The 5 motions are tilt left, tilt right, tilt up, tilt down, and shake. The first 4 produces light and sound according to the color as shown on the screen. The last motion is to cancel out if the motion is different from what was intended. The microbit has 4 functions we would like to highlight. First is the LEDs. Before the motion is locked in, the LED will blink 5 times. After that, if there's no cancellation, the LED will light up for 2 seconds without blinking. We also program the buttons on the microbit. Button A is for the teacher to see if see the previous answer if needed, while button B is to clear the previous answer that was stored. Lastly, the display on the microbit itself would indicate the direction of motion. We programmed the microbit using the Miko editor by Microsoft. The IDE supports both Python and JavaScript. We use Python. Microbit was chosen as the program was easy to access through an online editor, and it had a full range of sensors that are already built in, which was useful during our prototyping phase because we did not need to buy additional sensors to add on onto a single microcontroller, and it also made it more things more compact than what it would have if we had to add on more. Now Johong will explain our prototype further.
Thanks, Agnes. Now I'll be moving on to our final prototype solution. After developing the functionality of our device, we use Velcro to attach the device onto the user wrist. First, the Velcro wristband is tightened and adjusted on the user wrist to ensure they are comfortable with it. Then, micro:bit with Velcro tape is secured on a Velcro wristband. Finally, the batteries are mounted below the band and connected to the micro:bit to supply its power. This assembling method allowed the users to attach the microcontroller and the battery separately, as it is easier for them to assemble the entire setup. With our device, the benefits it brings to our wearer includes the wearer being able to observe their intended responses from the lights and sound emitted from their wrist areas. Other than that, our device motivates the wearer to use the device due to the interactivity of the lights and sounds. Also, the users can train their motor skills as the device only triggers when the motions are above a certain threshold. The device is designed to be lightweight and portable to allow them to be used outdoors. The design of our device is catered to students with special needs, so we intended to make it as compact as possible by limiting its size to just only around the size of a watch. The whole device is just weighed around 70 grams to prevent causing tiredness from using it constantly. Also, the brightness of the LED lights and the volume of sound are adjusted to ensure they do not cause distraction from children. 2 AAA batteries are chosen to be our power supply as they are just enough to power the microcontroller and the LEDs. Our device also brings benefits to the teacher. The teacher is able to know the students' responses by observing the LED colors and the sound emitted from the device. Students can also operate it independently without their helpers. Moreover, teachers can test out the students' understanding by asking them to perform a specific motion. Also, the device stores the last response that the user indicated, which allows the teacher to look back. There are still some limitations to our prototype, and they will probably make the device non-user friendly. The device is slightly bulky because of the micro:bit extension board. Secondly, the AAA batteries we are now using are non-rechargeable. Replacement is needed when they run out. The device is also not durable enough to withstand any collision. Lastly, due to the odd-shaped micro:bit and its extension board, casing is hard to build to accommodate them. Thus, we are currently exposing all the components and wiring to the surroundings. To optimize the end-user experience, we plan to improve our prototype to be more compact and wearable-friendly. Also, we intend to produce a casing by using 3D printing to increase its durability. And rechargeable LiPo batteries will be used to replace the AAA batteries to achieve sustainability. Lastly, an on and off function is to implement it into our future prototype. With that, our presentation comes to an end. Thank you for listening. We are now open to questions.
Thank you, Team Ben, for your presentation. Maybe I can start off by asking one question. So what was your biggest takeaway from working on this and to like creating the idea for this product?
I think the key takeaway from this project is the empathy towards the beneficiaries. Like, we really need to think about how the students will use the device. Hence, we need to put ourselves in their shoes to test out the device based on the movement those students can perform. Like, we realize that we should not take everything for granted, as we really need to appreciate what we have now. And being able to contribute to our engineering knowledge to the society, I believe we've picked up a lot of engineering skills, and it is really a great opportunity for us to learn more things.
I think Jeffrey also has something to add about your takeaways.
Yep. I think one of the things that we sort of intend to improve on as well in the future is to do a bit more testing with our users. So we haven't been able to do the testing with our users due to COVID restrictions. So in the upcoming few months, we intend to hopefully be able to get some testing done so that we can get a bit more user feedback as well. So I think this links back to the point on empathy as well.
Okay, thank you for sharing. I think someone had a question. So Professor Jakob had a question. So his question is, your device works on deliberate motion, but what if the motion by the beneficiary isn't deliberate, and how would the teachers be able to know this?
So for the deliberate motion, I and I think we left this out, is that how we utilize this wearable device is when it's from the teacher side, because primarily like this device is we created it for a classroom setting. We are trying to figure out how we can go beyond the classroom, but primarily it's for the classroom setting where the teacher asks a question, because from the interactions that we saw in the class, it was mostly the teachers asking a question, trying to see if there's a response from the user. So we also included the shake function to in case if the motion was not intended, but this device is mostly for the teacher is the one prompting the question first before seeking a response. Yes.
We thank you for the question. Thank you for answering it. I think there was one more question, but if I'm not wrong, Jeffrey answered this. Maybe you can clarify again. But the question is, was this prototype tried out with the students?
No, because not yet. Like we are hopefully waiting for the restrictions earlier, because currently it's only 2, and we are hopeful. We hopefully will want to go down, and that will go beyond the limit. So we are hoping when the restriction go down, that we can go and test it out. We went for the visit to the school site visit before the restrictions decreased to 2. So we managed to at least see the interaction within the class with the teachers. Yes.
Okay, thank you for your presentation, and we hope that you will get to test your product on the students soon.